Hey, how's it going? This is Qasim Wani, back with another reinforcement learning video. This one is actually going to be more exciting and fun than the previous one. If you're following along in the playlist, this is the second video on RL. The first video was on the derivation and the intuition behind Bellman equations, where I spent a couple of minutes explaining the situation, the motivation behind it, and the remainder of the video actually deriving it. But this video is actually sort of the more practical side of things and actually showing you an example of where Bellman equations are used, the example being the Monte Carlo situation, the Monte Carlo control methods, to deriving an optimal policy by running your agent over multitude amounts of iterations or episodes. So this example, all MDP processes go through must be episodal in the sense that they should terminate at a certain point, either if certain task is completed or if some information is lost or some task fails to meet the requirements. And in this video, we'll be talking about, in brief details, about the objective of this RL agent, as you can see in the screen, and then we'll just share very quickly the actual application and how to incorporate this. So without further ado, let's get started. And if you're following along in the playlist, I really appreciate you subscribing and showing some love to this channel. I'll try to make some videos per week. It's not really decided as to sticking with a regular day of the week, but it's something. All right. So in this video, as mentioned, we'll be talking about the designing an agent that can learn to perform a specific task. In particular, we'll be talking about a classic control agent called the cart pull. And cart pull is essentially, as what it sounds, it's basically you have this sort of this body of mass or a cart, and on top of that you have this pull. And the objective for your RL agent, your agent has to sort of balance this pull on this cart, and if it does, congratulations, for every time step t that it manages to balance the pull, you get a reward of +1. And as soon as it cannot balance it, the episode terminates, making it an episodic task, with the maximum reward that you could get in V1 is 500. And I believe V0 has somewhere between 125 to 200. I'm not totally sure on the exact numbers, but that's the idea: is how can you manage to build an agent that can learn from the environment to balance this pull on the center of its own object, right? And to show that, you can see this sort of this GIF or GIF in here, where you can see the cart trying to manage the pull per episode. And to get more information about what information is being transmitted from OpenAI Gym, to sort of the environment, to the console or to the agent, we can just check it out over here. And you can see that, for each state you have 4 observations, and they're all continuous in the continuous time domain. And they include the cart position, cart velocity, pull angle, and the tip velocity of the pull. And there's only 2 discrete actions that you can perform, which is either pushing the cart to the left or to the right. And so that's it in terms of the actions that you can perform. It's a discrete object of size 2. The action space is 2, and it's either pushing the cart to the left or pushing the cart to the right. While as the observations are more continuous, but they do have a maximum and minimum boundaries. But for velocity, and for the velocities, it's infinite. That's the gist of it, and this can be found in the cart pull V0 GitHub README for the wiki for OpenAI's Gym. All right. So without further ado, let's just get right into the sort of the video. Um, and let's just demonstrate. I've already implemented this. I won't be sharing it into details, but sort of I can just share you the policy itself. So what we'll be doing is building it, without using any DQN or any sort of Q-learning, no temporal difference or of anything. It'll be a very simple, naive approach, which is collecting, iterating over over a large number of episodes and building this sort of action value or the state action pair are also known as a Q table. And the Q table essentially will be comprised of, given a state and an action pair, what was the reward that came out of it. And you build this Q table and sort of it generalizes to the optimal policy, right? And that is just purely based on the fact that given the number of episodes tends to infinity, due to the law of large numbers, your Q table, your policy, P would approach P prime, or the optimal policy, right? And this is done using the model-free prediction, which is, an example of it is the Monte Carlo method. And that is exactly what we'll do. And initially, to start off with, before implementing the Q table, let's just see what happens if you put the agent in this environment and randomly randomly select any of the actions, 1 or 0, either move it to the left or to the right. And in that case, you're obviously your agent is not learning anything, and it was just, it's just random motions. And let's actually demonstrate it by running this code cell over here and see what the average reward that you get for n number of iterations is. So let me just tweak up the numbers just a bit. Let's say we're going to run it 50 times and just see the average reward that you would get for running it. Instead of 50, it seems like it's too much. Let's just do it for 25. And let's just see. So as you can see over here, this is our agent running this simulation based on the policy, which is random, completely equiprobable random policy. And as you can see, after 25 episodes, the average reward per episode was about 19, right? So it's basically lasted for 19 time steps. With each time step that you're stable for, that you stick in the game for, you get a reward of 1. And at this point, it's clear to know, like, how does the episode terminate? There's 4. I guess there's 2 to 3 criteria. The first being the angle. If, according to the OpenAI, the team at OpenAI, they define, actually it's adapted from the book by, let's see, I think it was adapted, this version of the card pull problem was adapted from the book on reinforcement learning by Bardo, Sutton, and Anderson. So the idea is on, so the how an episode ends is if either of the 3 criteria are filled, are checked off. If the angle, so the first one is if the angle of the pole is greater than 12 degrees from the center, right, in either of the directions. So if the pole, and this is for V1, I'm pretty sure it's the same for V0, but don't quote me on that. So if the angle of the pole is greater than 12 degrees from center on each side, then the episode terminates. And so you have a range of 24 degrees in total. And also, if the position, the center point of the card is greater than 2.4 units away from the center of the grid, which is over here, that means that the episode terminates. And lastly, if the reward that you have accumulated is greater or equal to 500, that means the episode must also terminate because you have met the full requirements of this task. And since this is an episodal task, it has a maximum amount of reward that you can get, and in this case, it is 500. So those are 3 ways on how an episode can terminate, right? And so, using the equiprobable random policy, it's obviously not going to produce a good result because you're not really gaining information at the iteration of every state in an episode. And so that's the equiprobable policy and how the reward was expected based on that. Now let's go to a more physics-based policy, which is based on the center of mass. And since it's clear to note at this point that the OpenAI gym observes physics and observes all the laws governing motion, right? So it's not anti-gravity based rules, but very realistic situations, although it's very different from real world, but the simulation is based on operating laws of physics. And using the momentum-based policy, it's basically can you extrapolate some information from the center of gravity of the pole with respect to, or the angle with respect to the position of the card itself, right? And the idea is if the pole is on this side, on the right side, it is leaning towards the right side. And to balance it intuitively, you would move yourself to the right side. So you move in the direction the pole is pointing towards, right? And that is incorporating the momentum and the center of gravity of the pole with respect to the cart, right? And that's a physics-based approach. And this is also clear to note that this is not going to be the optimal policy for 2 reasons. One, it violates information induced to the agent, meaning that in the classic RL scenario, putting in the sort of information sends this bias to the agent, and which is not what we want to have. We want the agent to learn such policies by themselves without a human interacting with the agent, right? So this won't be the actual way the agent will learn. The agent will learn by trial and error. But just to see that this is something that the agent could learn, potentially learn, is something noteworthy and something to state. And let's do the same thing. Let's run this policy 25 times, given this policy, and let's run 25 simulations, 25 episodes, and let's see how that goes. So as you can see now, the agent is performing much better than random policy, and it's basically stating that if I'm on this side, move the cart in that direction. And as you can see, wherever the cart is pointing to is where the agent is moving. And as soon as it's done, you can easily see that at the average reward after 25 25 episodes was roughly 39, right? So it's way better than random chance, almost twice as good, but you want it to be much better, right? It still doesn't take into fact of the more information that you get from each state. And some of the information that you get from each state is sort of, as mentioned earlier over here, the card position, velocity, angle, and the velocity of tip, which is something that can be observed over here. And at this point, it's also clear to note that this is an RL agent in continuous domain, and you want to discretize it, right? So you want to go from this continuous system and convert this information, the signal, into a discrete version. And the process of going from continuous to discrete domain also tends to lose information. But if your discretized bins, if you're binning it at a very small amount, then the information isn't technically, although it's lost, you can still gain some significant information about it without losing a lot of data. But if you were to discretize, let's say, if you had sort of the scenario where you were tasked to record the age of people in a database, but the only categories you had was, is a person less than 30 or is a person greater than 30, then you're obviously going to lose a lot of data because you now lost the exact number and you're just left in 2 categories. But now if you have sort of 5 categories, such as is a person between 0 to 10, 10 to 20, 20 to 30, and so on and so forth, you now have a much better estimate. And although you're losing, data from the environment, from the collecting of the samples, you have better information than the past policy, right? And that is sort of what it means to discretize it. And so that's what I implemented over here. You're discretizing it, and this is based on the equal width approach, and it's based on the boundary mean, such that if the mean of 2 boundaries, if the mean of the state is between, if the state is between the mean of the low and the high boundary of the bin, it would go with the lower boundary than the higher one, right? And that's what happens over here. And so, that's what happens when you discretize it. And so now, the meat of the video, the meat of this task is the MC control policy generalization, or the generating a Monte Carlo based solution. And we're going to develop a Monte Carlo based solution using Epsilon greedy approach with constant alpha state. And the formula for that is quite simple. It is basically this: given the current Q table value, given the current action, the state value pair, the state action pair, can you sort of gain more reward, you can gain more understanding and update the Q table such that the Q table is dependent upon the current reward plus the discounting return, right, into the future. And the way you do that is basically by getting the value of the current state action pair and updating it with the current value plus sort of this augmented discounting, or regularizing it with this alpha with respect to the loss between the immediate return from running that state with the current value of the state itself, right? And this is based on when you're exploring, or when you're exploring your environment than when you're exploiting, right? And this is based on the idea of the Epsilon greedy approach, which is basically intuitively what it means is that let's describe Epsilon greedy approach intuitively in like 40 seconds. Say you're new in town, and say you're new in town, and there's like 6 restaurants in the city, and let's say today, since you just moved in, you're tired, and you just go into restaurant number 1. Right, and let's say the outcome of that result of going in there was very good. You actually enjoyed the food, and you have recommended that restaurant to yourself in the future. Now you have explored, right? You've explored the state space, the sample size of actually the population of 6 restaurants in that city, and you picked one. And you liked it. You picked one from random. You didn't really have much choice. Maybe, let's say, the names of these restaurants didn't matter, right? So if it was Thai or Chinese, that may have given you a bias. Maybe you prefer Asian food more than European food. But let's say in the case that the only information you were given was the location of the restaurant, and they were all at reasonable distance from your house, and the only other information that you're given was the food itself, which was after you visited the restaurant. And now what happens is, now that you've explored the state space of one restaurant, you really liked it, and let's say the reward was a positive sum outcome. Now you're now left in this dilemma. The next time you do go to having dinner, having night out, you're left in this dilemma between choosing to go to the same restaurant, which is exploiting your past information, past knowledge, versus exploring other outcomes, other restaurants, and maybe those restaurants tend to be better than the one that you had. And this is known as the exploitation dilemma, where what does an agent do in a scenario where it can exploit its current observation, current knowledge, versus explore other environments or other states given the current state. And this is based on the idea that you want to maximize the expected return, right? And if you're currently, when you have explored one object, one outcome, you get a return of 1. And do you stick with that, or do you explore, or at a risk of getting the reward of 1 with potentially either getting more reward or getting less reward by exploring other places? And this is the idea behind exploration dilemma. And so the way you do this is you want to make sure that you don't continuously keep exploring the whole space, and you also don't want to be very, tunnel-eyed and focused and just exploiting whatever you have. To balance this, you basically put in this parameter epsilon, which manages how much you want to split your sort of vision into exploring and exploiting, right? And the smaller the value of epsilon, the more you sort of exploit your observations. The larger the value of epsilon, the more you explore your environment. And epsilon is, it's a stochastic measure, so it's from 0 to 1. And that's sort of the general idea. And you use this, and you use it frequently in the Monte Carlo methods as a model-free prediction tool to sort of generalize and get a much better understanding of your environment. And, long story short, TLDR, that's kind of the story that we use with the MC control policy generation, where you use this constant epsilon with, constant, when we're using epsilon with a constant alpha for getting sort of more information about the world in a much better way. And the reason why we use alpha is because you want to, so alpha is basically another way, it's basically a biasing factor, which sort of takes the current value that you have from your Q table and also the value that you have from the incoming state or the incoming return from the state or the decision that you made. And you don't want to sort of put the prior knowledge as the be-all and end-all of your whole situation of your agent, but at the same time, you don't want the incoming knowledge to be also very important, such that it replaces all the past knowledge that you've gained when you're presented with that state and that choice. So alpha is sort of another sort of hyperparameter that you can tune, which essentially balances out past experience with incoming information, right? And so alpha is another great way of sort of balancing out information. And, so the rule of Monte Carlo processes or control methods state that given that a task is an MDP, so it needs to obey the Markov decision process, right? That's a given. Given that is true, if the number of episodes approaches infinity, you are guaranteed that your policy pi will converge to the optimal policy p prime, p star. And since there's limitations on compute and time, you cannot run your algorithm for an infinite amount of times. But in this case, we ran it for a large amount of times. That may seem reasonable to attain a very good policy, such that p prime may or may not be the optimal, but it's definitely better than pi itself, right? And we ran it for around 500,000 episodes, and sort of that's the way we went with. And we used the value of alpha or epsilon as 0.03, such that it focuses more on exploring initially. So initially it explores a lot, but as epsilon gets larger and larger, as the number of episodes increases, the value of epsilon decreases such that it prefaces on exploiting, right? As we said, the smaller the value of epsilon, the higher tendency you have to exploit current observations. And so once I ran it for 500,000 episodes, it's usually running on CPU-based local session took me close to 4 to 5 hours. And after the model was trained, the amount of parameters or the amount of values in the Q table were close to 192,000. Right? That is a lot, but it's nowhere near running it for more episodes. And yeah, so after running it, testing, so now we are left with this choice of what value of epsilon to go with. Do you go with a default value, or is there a better value that would probably better help in the model converging towards pi towards the optimal policy pi star? And in that case, we can perform hyperparameter tuning. I did the classic grid search approach. You could try random search, and that's what I actually did initially. I tried random search, but then it became very clear that as the value of epsilon increases, the average return reward that you get also decreases due to the fact that now you're exploring, but you also have this information about the state that you're in that it has a diminishing marginal return. And as you can see that, this is empirically proven such that as epsilon tends to the stochastic measure of 100% or 1, the reward for n number of states where n equals 100, n episodes decreases sort of exponentially, right? As the value of epsilon in this case optimal is at 0, and the reward we get is very close to 450. Remember that the maximum reward you can get is 500. Above that, the outcome of the agent terminates, the episode terminates, and we proved that empirically. Yeah, so yeah, as you can see, after running it, with the optimal epsilon value, it was close to 442. Now, it is also important to note that the reason why we don't have an average of 500 is because we didn't run our episodes long enough. 500,000 is a lot, but 5 million is a lot more. This order of magnitude increase of episodes would give us a marginally better result in the value of the average reward, and obviously a better policy which would tend even more closely to the optimal policy. And you know what, let's actually demonstrate it, because enough of me talking, and let's actually prove that the model that we generated using our method and control actually sort of performs better. And I'm running this 10 times instead of 25 like other cases because it will take a lot of time. And I wanted to make this a very quick video, but unfortunately, I got a big mouth, so sorry. But let's just run it for 10 times. That was a bad joke. Yeah, so let's just run this for 10 times, and with the Q table that we just learned about, running it for 500,000 times, and let's actually run it and see how the model or the agent performs. So I'm just going to run it, and as you can see over here, as you can see over here, our agent is performing way better than the past past policies that we use. So it's way better than equirandom probable policy, obviously, and it's also way better than the momentum-based physics approach of using center of gravity policy. And it is also incorporated and has actually learned by itself how gravity sort of affects a scenario, right? As you see, as a cart is moving in one direction, as a pole is moving in one direction, the cart actually tends to move in that direction and balances things out. So you can tell that it has actually learned from scratch by itself about how to keep an object stand still in this sort of environment, right? Just by understanding the laws of physics and understanding the scenario it has been presented with. And this is sort of the idea behind reinforcement learning: is how can you, without explicitly programming an agent, how can you make an agent learn a sort of policy that can help it attain maximum expected reward? And after just 10 iterations, you can see that the average reward that you get is 423, right, or 422. And so sort of that's sort of the gist behind this. And I guess, yeah, now that I've sort of explained the general idea behind all of this, and I really hope that may or may not help you understand and get a much better field of vision or idea on RL tasks and agents. And if you did enjoy this video, despite it being long and stretched out, and I really appreciate you to support the channel by subscribing, and whatever unique way you find helpful. But yeah, thanks for watching. I guess, yeah, see you.